I hope this is visible.
Yes.
Okay. So, hello everyone. This is a great pleasure for me to introduce Professor Yu Han as the opening speaker of the second session of the lecture series on Cryo-EM and related techniques. Professor Han has earned his PhD in inorganic chemistry from Jilin University, China in the year of 2003, and between 2003 and 2008, he worked in the Institute of Bioengineering and Nanotechnology, Singapore as a postdoctoral fellow and later as a research scientist. He is currently an associate professor in the Department of Chemistry at King Abdullah University of Science and Technology, Saudi Arabia. Professor Han is a materials chemist and his research is focused on nanoporous and nanostructured materials, including ordered mesoporous materials, hierarchically structured zeolites, porous organic polymers, porous carbons, and metallic plasmonic nanocrystals. His ability to precisely control the structure and morphology of these materials promoted his great success in developing novel applications for them in gas adsorption separation, heterogeneous catalysis, and nanophotonics. For his outstanding research contributions throughout, Professor Yu Han has received Young Scientist Award of Singapore in 2006, Thomson Reuters Research Fronts Award in 2008, to name a few. Professor Han, of course, is an expert in electron microscopy and electron tomography, using which he has successfully solved or identified some complex nanostructures. He has published numerous journal articles, and these papers have been cited over 10,000 times. With this brief introduction, I will stop sharing my screen and I will like to welcome Professor Yu Han.
Thank you very much, Amrita, for your very nice introduction. I think everything is fine except the the publication record is out of date. It's 5 years ago data. So, but it doesn't matter.
Yeah, I'm sorry.
No worry. Yeah, that's fine. So I'm going to share my screen.
Yeah.
So let me. I hope you can hear me well. And so can you see the screen?
Yes, very well, and we can hear you well.
Okay, great. All right. Yeah, again, thanks for the organization and thanks for the introduction. And good evening, everyone. First of all, I'd like to thank Professor Pradeep for inviting me to deliver this lecture today. And I feel very honored to be part of this high-profile, well-organized lecture series. And the title of my talk today is Atomic Resolution. Let me change the. Okay, atomic resolution imaging of sensitive materials using ultra-low dose transmission electron microscopy. So high-resolution transmission electron microscopy, or HRTM, is one of the most powerful characterization tools extensively used in both material science and life science. As you may know, a modern TM microscope can provide sub-astron resolution. That is high enough to resolve individual atoms. Well, unfortunately, however, a large number of materials are conventionally considered unsuitable for TM characterization. The reason is very simple. They are sensitive to electron beam irradiation. So once exposed to the electron beam, their structure will be immediately damaged. So we don't have a chance to record their intrinsic structures. And this is the so-called beam damage effect or beam damage problem. So actually many materials have this problem. For example, porous materials like zeolites, morphs, COFs, or organic crystals, or polymers, proteins, supermolecular structures, hybrid materials. Many materials has this problem. So we call this kind of material electron beam sensitive materials, or simply it's beam sensitive materials. So actually for a beam sensitive material, the structure information contained in the HRTM image is not determined by the resolving power of the microscope, but by the beam stability of the material. That is, how much structure integrity can be preserved under the imaging conditions. The more severe the structure damage, then the less the structure information we can see, right? Makes sense. So today, I'm going to talk about how we use our recently developed ultra-low dose technique to achieve high-resolution TEM imaging of this kind of beam-sensitive materials. So in this talk, I will mainly use metal organic frameworks, MOFs, as typical examples to demonstrate the effectiveness of our method. Right? This is because MOFs are very well recognized as extremely sensitive to electron beam, and the HRTM of MOFs was not possible prior to our study. Okay. Well, although I use MOFs as examples to demonstrate how effective our method is, well, our method is not limited to imaging MOFs. It can be generally applied to other sensitive materials as well. At the end of my talk, I will show you some examples. Okay. So I don't know the background of the audience today, so allow me to briefly introduce what MOFs are. So MOFs consist of metal clusters that are connected by organic linkers or organic ligands to form three-dimensionally crystalline structures with very well-defined nano-sized pores in the structure. Okay? So MOFs are crystalline materials, MOFs are porous materials, and MOFs are organic-inorganic hybrid materials. And the most important feature of MOFs is that they have diverse and designable structure. So because of MOFs can be easily designed with desirable structures, porosities, and functionalities. So they have shown a lot of important applications in many different areas, including gas storage, gas separation, catalysis, sensing, and many others. So MOFs, as I said, MOFs are crystalline materials. To study a crystalline structure, the first choice is, of course, diffraction, right? Diffraction can resolve the crystal structure in reciprocal space. Well, the outcome of diffraction is a unit cell. The unit cell represents the averaged bulk periodic structure of the crystal. Okay? So alternatively, we can also study a crystal structure in the real space by imaging technique, for example, by high-resolution TEM technique. Well, the advantage of imaging is that in addition to the periodic bulk structure, imaging can also probe the local non-periodic structures. For example, the crystal surfaces, the grain boundaries, the structure defects, the gas molecules, and so on. Okay, so these kind of structure features are local and non-periodic, so they are not visible. They are not visible in diffraction. They are not visible in diffraction, but they can be directly observed by imaging. Oops. Well, let me back to the topic of MOFs. So MOFs have more than 20 years history, right? However, if you look back at the literature of the past 2 decades, you will find that there are very few studies on the local structure of MOFs. This is not because local structure of MOFs are not important. Actually, they are very important for applications. They were not studied. It's only because there are no suitable characterization tools. As I mentioned earlier, HRTM is a good choice for probing the local structure, right? But MOFs are extremely sensitive to electron beam, and they cannot be investigated by conventional HRTM. So here I give you one example to explain this problem, this the so-called beam sensitivity problem. So here you see this is a TM image of a MOF called ZIF8, okay? And this image was acquired with an electron dose of about 1,000 electrons per square astron, which is a very typical electron dose used for conventional HRTM. However, as you can see from the image, the ZIF8 crystal structure has been completely damaged or destroyed under this condition. So we can see in the image, we just see amorphous particles, right, without any useful information. We know ZIF8 are highly crystalline, but we don't see the crystal structure. We only see amorphous particles because the structure has been damaged. So this result explains why conventional HRTM is not suitable for imaging morphs or other beam-sensitive materials. Okay, so to quantitatively understand the beam sensitivity of ZIF8, we conducted an electron diffraction diffraction experiments to monitor the structure evolution of ZIF8 under the electron beam irradiation. And it turned out that when the cumulative electron dose reached about 15 electrons per square atom, the structure damage occurs. So this means if we do want to capture the crystal structure of ZIF8, we must control the total electron dose below this value. Well, this value, as you can see, this value is about 2 orders of magnitude lower than the electron dose needed for conventional HRTM. So how to reduce the beam damage effect? In fact, the mechanisms for beam damage are quite complex, including knock-on damage, heating effect, radiolysis effect, and so on. Okay? So one can use the so-called low voltage TM technique to reduce the knock-on damage. Okay? And this is this kind of low voltage TM technique is particularly useful for imaging two-dimensional materials, 2D materials. However, the low voltage will lead poor resolution and also short penetration depth. And more importantly, low voltage sometimes may even give negative effects if the damage is governed by other mechanisms than knock-on. Okay? So low voltage TM cannot be generally applied to all the applications. And likewise, one can perform TM at cryogenic temperatures. It's so-called Cryo-EM, right? You can low down the temperature of the operation, so you can minimize the heating effects. However, this doesn't help to reduce the damage caused by other mechanisms. So similarly, low temperature or Cryo-EM is not generally applicable to all the applications. So here we propose that regardless of the exact damage mechanism, the damage is caused by electrons interacting with the specimen, right? So we can acquire, if we can acquire images with sufficiently low electron dose to capture the structure before damage occurs, then this problem can be largely solved, right? So we decided to develop low dose technique, not low voltage, not low temperature, but low dose. Well, this idea sounds easy, but it's very hard to realize. If you recall the electron dose a morph material can withstand, yes, only 15 electrons per square atom, then you may realize that imaging with such a low dose at a reasonably high magnification actually require a very, very sensitive camera to render useful information with only a few electrons per pixel. Okay. Conventional CCD camera cannot do the job. So conventional TM cannot be conducted at such a low dose condition because with such a low dose, the signal to noise ratio of the image will be too poor to show useful information. So this situation is just like, taking a photo picture in a dark room where, because the light illumination is limited, so we can't see much in the picture, right? So to solve this problem, we need to develop new imaging method, which we call ultra-low dose HRTM. So today, because the time is limited, so I will make a long story short. So simply, we solve this problem in 2 steps. In the first step, we demonstrate that a new type of camera is called direct detection electron counting camera can form useful information, useful image with the low dose conditions required by MOFs or by other beam sensitive materials, extremely sensitive materials. Okay, because this new type of camera is very sensitive. And in the second step, we develop a suite of methods to improve the efficiency and the quality of the ultra-low dose HRTM enabled by the new camera. Okay, so these methods are about image acquisition and image processing. The first method, for example, allow us to quickly find the zone axis of the crystal in TM so that we can minimize the electron dose used for the zone axis alignment so that we can protect the structure from being damaged. And the second method can retrieve the impaired image resolution due to the specimen movement during the exposure, okay? And so we can enhance the final resolution of the image. And the third method allow us to properly process the image to make it more interpretable. As you may know, a normal HRTM image is not directly interpretable, so you need to process the image. Well, to process the image, you need to know the exact imaging conditions. Well, the third method allows us to do so. So after the image processing, the image become more interpretable. All right. So yeah, again, because of the time limitation, I cannot explain or elaborate all the technical details. Well, if you are interested in these methods, please refer to our publication in 2018. Okay, so here simply the first step is about the use of a new camera and a use of a new hardware. Well, the second step is about the development of some new methods or softwares. Okay, so taken together, we are now able to image beam sensitive materials with HRTM at atomic resolution. The next couple of slides are about the working principles of the three methods. So I have to skip them, and and I will directly show you with this new technique established what we can do from the chemistry perspective. Okay, I will show you some examples. And after we establish this ultra low dose HRTM technique, we have used it to image a number of MOFs because, as I said, MOFs are extremely sensitive. So it's a very good example for demonstration. Okay, so we have successfully imaged a number of MOFs materials, and our focus was on their local structures, including the crystal surface, the interface between crystals, the gas molecules encapsulated in the MOF structure, and the missing linker, missing cluster defects, and some others. Okay, I will, in the next maybe 20 minutes or so, I will give you some examples. So before studying local structures, we started with the bulk structures. So most MOFs have known crystal structures that are solved by X-ray diffraction, single crystal X-ray diffraction. So in this sense, imaging the bulk structure doesn't provide additional structure information, right? However, imaging the known bulk structure is necessary and actually very important. This is because the known structure can be used as a reference, which allow us to confirm that the used imaging conditions is safe enough to preserve the structure from damage. And therefore, this ensures that the observed local structures are inherent structures, not the result of beam damage effects, right? So it's meaningless to image local structures under conditions that can damage the bulk structure, right? So this is our logic. We don't know what conditions, imaging conditions are safe, so we use a known bulk structure as a reference to prove the imaging conditions are safe, and then we can image the so-called local structures, because nobody knows what local structure look like, right? So we have to make sure the imaging conditions will not bring the structure damage. This is why we always, whenever possible, we always start from the bulk structure, okay? And this is a HRTM image of a morph called UIO66. And this image was acquired with a dose about 10 electrons per square angstrom, very, very low dose condition, right? And the image resolution is about 1.5 angstrom, about 1.5 angstrom. This high resolution indicates that the structure is well preserved. So the processed image shows a perfect match with the 110 projected structure model of UIO66. The important structure features in this projection, including, for example, here, the triangular channels, the inverted triangular channels, and this is the zirconium clusters, and here are the organic linkers. All these structure features can be clearly observed in the image. And this, you see, here we have the triangle channels, invert triangle channels, zirconium clusters, and organic linkers. And in some local places, you can even see the benzene rings in the cluster, in the organic linkers. Okay, so this result confirm that the crystal structure of UIO66 is very well preserved under the ultra low dose condition we use. And after we confirm that the imaging condition is safe from the bulk structure, we move forward to look at the crystal surfaces. Interestingly, we found that the surface termination mode of UIO66 is facet dependent. The major 111 surface over here are terminated with organic linker. Okay, well, at these truncated surfaces, which consist of the 100111 kinks, at these kink positions, actually the outermost surface is terminated with metal clusters. You see very clear here. The outmost surface is consists of metal clusters without organic stuff. Yeah. So two types of surface termination: organic linker terminated surface and metal cluster terminated surface coexist in this material. And we also studied the crystal surface of another morph. It's called mu101. And mu101 is a mesoporous morph. So it has a very large pores and very huge unit cells. In each single unit cell, there are more than 5,000 atoms. So very complicated structure. Yeah. Well, following the same logic, we started with imaging the bulk structure to confirm the imaging condition is safe. Right? And as I said, mu101 has a very complicated structure, but still our image show perfect matching with the projected structure model. This is our image. This is the structure model, and this is the simulated potential, potential map. So all the main structure features, like these mesoporous cages or the surrounding smaller channels and clusters, even the metal clusters, can be clearly identified in the image. So then we study 3 mu101 samples that were synthesized with different additives as modulators. The 3 modulators are HF and acetic acid and a no modulator, 3 different synthetic systems. Okay, and it's known that the modulator can influence the crystallinity of morphs and their crystal size, but no one knows actually modulator also has influence on the surface structure of morphs, because before it's not possible to probe the surface structure, so nobody can study the effect of the modulator on the surface structure. But now we can look at the surface of the crystal synthesized from different systems with HRTM. So here we use the completeness of the mesoporous cages to describe the states of the outermost surface. And we identify 3 different types of surfaces in these samples. As you can see from the image D E, and F here. Okay, so after vacuum drying at 150 degree, the sample synthesized with HF, you see this one, show very open cages at the crystal surface. Well, in contrast, the sample synthesized with acetic acid show completely closed cages on the surface. And the sample synthesized without using any additive show a state in between. So we identify three different surface structures. And another interesting finding is that during the vacuum drying process, only the sample synthesized from with HF has their crystal surface changed from closed to open. Well, the other two samples retain their original surface structure. So this observation suggests that the sample synthesized with HF has some different property from the other two samples, and it should have lower thermal stability because this surface structure change is driven by drying at 150 degrees. Okay. So to verify this speculation, we conducted in situ heating XRD experiment, and the result confirms that the sample synthesized with HF is more sensitive to thermal treatment and prone to structure change as compared to the other two samples. And we observe a phase transformation from mu101 to mu53 for this sample, starting at about 120 degrees. Well, this phase transformation doesn't take place in the other two systems. So in addition to the surface structure, we have also used HRTM to probe the interfacial structure formed by assembled ZF8 crystals. And ZF8 nanocrystals tends to assemble through the intergrowth of the 110 surfaces, forming a coherent interface like this. Okay, so here is a TM image showing such an interface. You can see the interface formed between two intergrown nanocrystals, right? And this image was actually the first ever atomic resolution image of a morph. And yeah. Okay, so if you still remember, at the beginning of my talk, I used a morph as an example to show you the beam damage effect, right? That morph was ZF8, the same morph. Okay, in the previous slides, I show you that under the normal conventional TM conditions, we cannot see anything in the image because the structure has been completely damaged, right? And now, using the low dose TM, we keep the electron dose at a very low level. In this particular case, the total electron dose is only 4.1 electrons per square angstrom. So at such a low dose condition, you see the crystal structure of ZF8 can be very well preserved. Yeah. So this is a very sharp contrast, right, to the previous example. Yeah. And this very well demonstrates the power of the low dose technique. So based on the HRTM image, we could analyze the interfacial structure, and the result shows that at the crystal interface, there is an additional layer of the imidazo ligands compared to the bulk structure. Okay, so this is the bulk structure model, and this is the structure model for the interface. Yeah, we see the difference. And therefore, at the interface, there are some large cavities generated. So this helps to understand how the assembly of ZF8 nanocrystals influence its gas transport property. Yeah, because when you have this assembly taking place, oops, something wrong. I hope not. Okay. Okay. So you guys can hear me well, right?
Yes, we can hear you.
Okay, great. Yeah. Okay, so yeah, because this kind of assembly can generate larger porosity at the interface, so we know how this kind of assembly behavior will influence the gas transport within the crystals. And okay, MOFs are very often used as host materials, right, to encapsulate gas molecules. However, it's very difficult to determine the exact location of the gas molecules in the MOF matrix. And some people even argue, how do you know you encapsulate gas in the pores rather than simply attached on the crystal surface? It's not easy to provide direct evidence for this successful encapsulation. Yeah. Well, with HRTM, we are now able to directly see where the gas molecules are. So we collaborate with Mario's group at Clarkson University, who immobilize this called single molecule magnets into a MOF called NU1000. So based on the size of the gas molecules, they predicted that this magnesis cluster, this gas molecule, should be located in the primary hexagonal channels because their size are larger than the secondary triangular channels. So they predicted the gas molecules should be located in the hexagonal channels. This is their prediction. Okay. Well, our HRTM observations confirm that this is indeed the case. As you can see from the image, discrete black dots are widely distributed in the MOF matrix. Right. Well, if you zoom in, you will see each black dots precisely reside in the hexagonal channels. Okay, yeah, this is zoom in of the area 1. This is the area 2 here. Okay, and if you zoom in other places, you'll see the same thing. The black dots very precisely located in the hexagonal channels. So, yeah, HRTM makes it possible to directly see gas molecules in MOFs. And we also studied structure defects in MOFs. The existence of missing linker and missing cluster defects in MOFs has been speculated from indirect evidence, right? But it has not been directly observed prior to our study. Yeah. So now with HRTM, we can see where the defects are and whether they are ordered, and if they are ordered, what's the domain size and how the domains are distributed within the crystals. All this information can now be obtained. Yeah. Okay. So in this particular case, we observed missing linker defects in UL66. Yeah. And because we get multiple image from different instances, so we can even reconstruct the missing linker defects from multiple images of different directions. And this is the reconstruction result. As you can see, this is a typical missing linker defects because in the perfect structure of UL66, the metal cluster should be 12 connected. That means each metal cluster is connected with 12 neighboring clusters by organic linkers. But here you see this is an 8 connected local structure. Yeah, that's why we call it missing linker, because the full organic linkers in the horizontal planes are missing. So this is the local defective structure. Okay, yeah, if you are familiar with the perfect structure of UL66, you know what I'm talking about. Yeah, so this is the direct evidence of the presence of missing linker defects in UL66. And to confirm this result, we use oh, sorry, I forgot to mention. We can see not only the missing linker defects, but more importantly, we can even identify the defects capping groups. Right? Yeah, the defects capping groups. The defects capping groups are format groups. Okay, yeah. And to confirm that the defective sample contain format groups, to confirm this result, we use carbon-13 labeled formic acid for the synthesis. And then we characterize the sample using HPLC, TG mass, and carbon NMR. And all these characterizations indicate that there are format groups in the defective UIO66. And these results are consistent with our TM reconstruction results. And interestingly, we also observe ordered missing cluster defects in the same sample. And ordered missing cluster defects in UIO66 has been speculated before based on diffraction data. Yeah, because in the diffraction data, people can see the symmetry forbidden reflections show up. Yeah, but with TM, we can see these defects and their distribution directly in real space. And we found that in comparison with the missing linker defects, the missing cluster domains are usually much smaller and only across a few unit cells, And this missing cluster defects always appear along with the missing linker defects. So we totally identified 3 types of defects in UIO66. This is the perfect structure model. This is the missing linker defect. And we identify another 2 types of missing cluster defect. So totally, we identify 3 defective structures in this sample. And their framework openness increase in this order from the left to the right. The framework is become more open from the left to the right. And another interesting phenomenon we observe in this system is that the defects evolve with crystallization. The sample collected after 1 hour of crystallization, this one, consists of very small crystals. Well, it contains a large number of missing cluster defects. As the crystallization time is extended to 1 day and then to 3 days, the missing cluster defects become less and less, while the missing linker defects remain. So correspondingly, the total pore volume becomes smaller, and the pore size distribution associated with the missing cluster defects gradually disappear. So more interestingly, with the extension of the crystallization time, the crystal size, as you can see, the crystal size also increases. So taken together, the structure defects evolves during the crystallization, while at the same time, the crystal undergo a ripening process. Okay, so all this information can only be obtained with TM study. The UIO66 system has been extensively studied, but this kind of information can only be provided by HRTM. Well, knowing this, the evolution of the defective structure, we can prepare a number of UIO66 samples with different defects types and concentrations, just by tuning the crystallization time and combined with so-called defect healing method. Right? And then we got a number of samples with different degree of defects. And then we use these samples as Lewis acid catalyst for the isomerization of glucose to fructose. And we found a clear correlation here between the catalytic activities with the degree of the structure defects. Okay, as mentioned earlier, our method is not limited to imaging MOFs, but also other sensitive materials. So due to the time limitation, I just quickly show you a few examples. So in 2017, we imaged a TPA-based COF. COF stands for covalent organic polymer. Okay, and this COF has a 2-dimensional hexagonal structure, and we identified 1-dimensional channels and the molecular building blocks in the image. Well, early this year, we used this technique to distinguish different topologies of 2 related COFs due to the presence or absence of the intramolecular hydrogen bonding. Either dual pore Kagome structure or single pore rhombic structure can be obtained from 2 otherwise totally same synthetic systems. And this example is a 2D nanosheets which are exfoliated from 3-dimensional supramolecular crystals. This is not MOF, not COF, but a supramolecular structure. Okay, so after exfoliation, due to the very low yield of the nanosheets, it's difficult to characterize their structures. And conventional TM didn't show any structure information because of the beam damage issue. Well, with our low dose TM, we confirm that these 2D nanosheets retain the original structure ordering in the parent 3D crystals. Yeah. Well, organic, inorganic, organic highlight perovskite materials are very important materials because of the optical and electronic properties, right? But they are similarly sensitive to electron beam as MOFs, so it's not easy to get atomic resolution for this kind of perovskite material. While using our method, we were also able to image them at atomic resolution. From the images, we can observe different cation orientations in a hybrid perovskite material, and we can also identify these N values of the RP-phased perovskite material, right? So perovskite is also manageable. All right, let me summarize what I have discussed so far. And briefly, I introduce an ultra-low dose HRTM technique, which is based on the use of direct detection electron counting camera, and the development of a suite of image acquisition and image processing methods. While using this technique, we have successfully imaged the bulk structure, local structure of many MOFs and other sensitive materials. Well, in the next 10 minutes or so, I will briefly introduce some more recent works and two topics. The first topic is about low-dose scanning TM, and then I will talk about how to prepare TM specimen from bulk sample or from real devices composed of sensitive materials. So scanning TM is also called STEM, right? Use the focused beam for imaging. So in comparison with normal TM, STEM has some advantages. For example, STEM usually give more interpretable image with better image contrast. And STEM also allow us to do microregion analysis by using spectroscopy techniques. Yeah. However, because STEM use a focused beam, so the instantaneous electron dose is much higher than normal TM mode. Therefore, STEM usually leads to more severe irradiation damage effects than normal TM. So for electron beam sensitive materials, STEM imaging is considered more challenging than normal TM imaging. But recently, a new STEM technique is called IDPC STEM emerged as a promising method for imaging sensitive materials. IDPC STEM has some unique properties. So first, compare with the standard STEM, like bright field STEM, dark field STEM, or HADIF, or high angle angular dark field STEM. These are standard STEM modes. Well, as compared with these standard STEM modes, IDPC STEM gives the best contrast and the highest signal to noise ratio under the same probe conditions. Okay, and second, compare with normal TM, HRTM, that requires image processing, very complicated image processing. The image contrast of IDPC STEM is easier to interpret. And in addition, IDPC STEM allows simultaneous imaging of both heavy and light elements. And this is another very important property. So these advantages are well illustrated in these images. So here we use different imaging modes to image a zeolite material, like absorb some hydrocarbon compounds in the channels, in the microporous channels. As you can see, this is the normal HRTM, this is the bright field STEM, dark field STEM, and this is the IDPC STEM. Okay, so as you can see, compared to the normal HRTM or standard IDPC, STEM, the IDPC STEM gives the best image contrast for the zeolite framework. And more importantly, it shows the presence of the organic compound in the channels very clearly. Yeah? You see in the channels, there are organic compounds. And this organic compounds contrast cannot be observed in other imaging modes. Yeah, so this is a very unique property of IDPC stem. It's sensitive to both heavy elements and light elements. Yeah, so IDPC is a promising low-dose technique and is suitable for beam-sensitive materials, and particularly useful for simultaneously imaging heavy and light elements. And MOFs are a good example because MOFs contain both metal that are heavy, right, and organic linker that are light elements. Yeah. So IDPC has potential to be used for MOF imaging. So we first apply IDPC to zeolites because zeolites are more stable, relatively speaking, stable. Actually, zeolites are also sensitive materials, but compared to MOF, zeolites are much more stable. So we use IDPC stem to image molybdenum atoms in zeolite channels. And based on the position of these molybdenum atoms and their specific interaction with the framework aluminum, so we can locate the aluminum atom in the zeolite framework. Yeah, this cannot be done by other technique. And we have also used IDPC stem to study a new zeolite. It's called EMM17. And this zeolite has 11 membrane channels, which are very rare in conventional zeolites. Most zeolites has 8 membrane, 10 membrane, 12 membrane. But this new zeolite has 11 membrane. And more interestingly, this new zeolite contains a large number of different types of structure defects. Yeah? And these structure defects can be clearly identified by IDPC stem. This material is rich in structure defect. You see a lot of structure defects. And well, MOFs are more, as I mentioned, MOFs are much more beam sensitive than zeolites. Well, the good news is that IDPC stem can also be used for MOFs. Here are the IDPC stem images of UIO 686 and MU101 with a resolution of 1.5 and 2.0 angstrom respectively. And these resolutions are as good as the resolution we observed using the ultra-low dose HRTM. Well, as mentioned before, the advantage of IDPC stem is that the images are directly interpretable without the need of image processing. Right? So yeah, the directly collected image looks like this, and we don't need complicated image processing. We can get interpretable image with IDPC stem. Yeah? And the image contrast is also very good. So personally, I believe IDPC stem has great potential for imaging beam sensitive materials, and this great potential should be further explored. Okay, so the last topic of my talk today is how to prepare TM specimen for sensitive materials. As you may know, for TM or STEM imaging, the specimen needs to be very thin, right? The thinner, the better. So usually specimen thinner than 50 nanometer is required for high-resolution imaging or quantitative analysis in TM. Well, since sensitive materials are traditionally considered unsuitable for TM characterization, so no attention has been paid, no attention has been given to their specimen preparation before, because they cannot be imaged anyway, right? Why to bother thinking about how to prepare the sample? Well, so in the previous slides, most of the examples I showed you were actually the MOFs images were collected from nano-sized MOF crystals without specimen preparation. Okay? However, in many cases, the sensitive materials we wish to analyze are in the form of bulk crystals rather than nanocrystals, right? So now the high-resolution imaging of sensitive materials has become feasible, has become possible with the new techniques developed. So now is the time to think about TM specimen preparation so that we can extend the application of this new imaging technique to large crystals, say micron size or even millimeter sized crystals. Okay? So the sensitive materials, for sensitive materials, actually the specimen preparation is not easy because mostly most likely the sensitive materials are not sensitive only to electron beam. They are also sensitive to other forces, and their structure can be damaged during the conventional TM specimen preparation process. For example, some morph crystals will become amorphous just simply by grounding or by crushing. Okay, so preparing a thin specimen suitable for TM imaging from sensitive material is a challenge to be resolved. Okay? So, and I will again make a long story short. I just show you what we have done. So recently we discovered a solution to this challenge. As you know, focused ion beam (FIB) is a common method for preparing TM specimen, right? And it's widely used in semiconductor industry. FIB to prepare specimen from the chips. And the advantage of FIB is that it allows site-specific and also orientation-specific extraction of the specimen from a bulk crystal or from a device, right? Well, FIB is normally performed at room temperature and is commonly used to cut hard materials, right? And is considered unsuitable for soft or unstable materials, okay? Because the ion beam can easily damage their structure, right? If the material are unstable. Okay, well, we found if we perform FIB at cryogenic temperature, say liquid nitrogen temperature, and this low temperature can effectively reduce the structure damage effect. So here we use a morph material called HKUST1. This is a millimeter-sized crystal, morph crystal, as an example to show you how a cryo-FIB works. Okay, so this is a workflow. This is a workflow that shows how the crystals was selected and mounted onto a TM grid and protected, and then finally cut and thin into very, very thin slice for TM imaging. So the slice, you see, this is the slice prepared by cryo-FIB. The slice prepared by cryo-FIB is thin enough for high-resolution imaging. As you can see here, very nice electron diffraction patterns, and the image obtained can give a resolution as high as 1.4 angstrom. This indicates that the morph structure was well preserved during the specimen preparation process. And in a control experiment, we use FIB at conventional room temperature, and the morph structure was completely destroyed. So we cannot get image for that specimen. Okay, so this result confirmed that the stability of a morph under the ion beam is greatly improved at cryogenic temperatures. So we propose that cryo-FIB is a promising method for preparing TM specimen for morphs and other sensitive materials. So from the image, we found that there are a large amount of structural defects that exist in this seemingly perfect crystal. Yeah, the crystal looks perfect, right? Yeah, but actually with TM, with cryo-FIB coupled with low dose TM, we can see a lot of structural defects inside the crystal. You see from the 111 zone axis, we can see a lot of planar defects, and this defect plane are parallel to the 111 plane, and we will report the structure details later. And here I just want to emphasize that such structure features in large crystals, large morph crystals, cannot be discovered if we don't have a suitable specimen preparation and suitable imaging techniques. So using cryo-FIB, we have prepared a TM specimen from a millimeter-sized hybrid perovskite single crystal, which allow us to acquire high-resolution image at nearly atomic resolution. And cryo-FIB can also be used to prepare a TM specimen from a real device. For example, in this case, we cut a very thin slice from a perovskite-based solar cell device. This is a real device, and this device is based on a single crystal perovskite as the active layer, active material. And this is the slice we prepared extracted from this device. And very interestingly, we found that when we characterize this active layer of the solar cell using diffraction, electron diffraction, we found that there are superstructure lattice, superstructure reflections observed in some local areas. Okay, so again, it's from a single crystal, but the structure is not uniform throughout the crystal. At some local area, we can observe the superstructure reflections in the electron diffraction pattern. And then we perform a more careful study, collecting electron diffraction patterns in a successful manner throughout the entire specimen. Okay, and then we found that the superstructure, is concentrated at this area, and the domain of the superstructure is about a few square microns in size. Okay, yeah. So here I just want to again emphasize that without using Cryo-FIB to prepare this specimen, this electron microscopic studies, including electron diffraction, TEM, all these studies of the bulk material or devices are not possible. Okay, I think I have overused my time properly. So let me end my talk by acknowledging the following people. So Da Liang, Yihan, Ling Mei, Xinhua, and Nini. Without their great efforts and hard work, we would not have been able to develop the imaging methods or collect the interesting images that I present to you today. And I would also give my special thanks to Dr. Ming Pan from Qatar, because it was Dr. Ming Pan who assisted us to try our idea of using the new camera for imaging sensitive materials at the very early stage of this project when we don't have our own camera. Okay, yeah. So I also thank many collaborators around the world for the opportunities to study their interesting materials, as well as for their experimental and theoretical support. And finally, I thank you all for your attention, and I'm glad to take any questions you may have, and thank you.
Fantastic. Great talk. Let me ask you a quick question as I need to leave a little bit. Sure. Well, today's with resolution, it is possible to see molecular structures, and in confinement. That is what zeolite is doing, and that is what you beautifully demonstrated. Now, okay. When something goes in, of course, there is breathing. Is it possible today to see structural changes when molecules get in and molecules get out? If so, in real time? That's one portion. The other portion is that how far away are we from really looking at orbitals?
Okay. I will take the first question first. My understanding of your first question is about how is it possible to image individual molecules and the molecular structure change in a confined environment. This is a very good point. Actually, imaging single molecules is possible, but if, for example, I already showed if the molecules like some hydrocarbon compounds are dissolved in a zeolite, they can be observed, but we cannot see the exact molecular structure or configuration. Okay, there are many reasons for this, because TM image is a projection image, so all the information along the projection direction they mess up. Okay, this is one reason. The second reason is that the contrast may not be enough, because most molecules, let's say organic molecules, they show a weak contrast. So now, at the best, in zeolite structure or porous matrix, we can see the contrast of molecules, but we cannot see their configuration or the exact structure. Well, alternatively, if we don't use porous materials to confine molecules, we can see single molecules and even see their configuration. We need some other substrate to immobilize the molecules. For example, I think in Japan, several groups they have done a fantastic job they immobilize single molecules onto carbon nanotube. Okay? Because carbon nanotube is made of carbon, so the contrasts are comparable with molecules. And this is, and also they, by using carbon nanotube, they can avoid this projection problem because it's just a single tube and single molecules. So in this way, they attach a single molecules in a single wall nanotube. They can see the molecules. They can see the molecule change, structure change induced by the electron beam. Yeah, this is I think this is the state of the art. So imaging single molecules using electron microscopy. It is manageable, but we have to design the experiment, very, very reasonably. And to your second question, to be honest, I have limited knowledge about, how to image the orbitals. And I know now it's possible with the DPC technique. We can see the charge the charge separation. Okay, but to orbitals, I think it's still too far to go.
Well, thank you very much, and Amrita will continue. I need to leave.
Okay, take care. Yeah, thank you again. Thank you very much for inviting me. Yeah,
Amrita, take it forward, please.
Yeah. So from the audience, if there are questions, I would request you to kindly unmute yourselves and ask the questions. Any question from the audiences? Okay, so I think there are not many questions, mostly because I think we all are awestruck and not really able to question, because the images and the resolution, the clarity, the ability of the tools, these are really a visual treat to us. So thank you very much for this lovely presentation, and the lecture was really engaging and easy to follow. So
okay. Yeah.
Yeah. So
it can work.
Yeah.
Okay.
Okay. So if there are no more questions, even if later on some questions you want to ask, you can always communicate. We'll try to have the answer. So thank